I am now switching to today's presentation, which is called UML, the Unified Modeling Language. And we can start by looking at different features of the diagramming inside UML environment. So we generally need to understand the purpose of various diagrams and what notation is available within these diagrams. The class diagram that I showed you earlier, which was taken from Wikipedia article, demonstrates the use of a single class with its name, data attributes, and operations. Over here in this demonstration, we have a class diagram for a ticket box application that obviously includes multiple classes. See that this diagram represents individual boxes as classes, and there are demos of various relationships between these classes. So there's quite a lot of different notations. So we'll try to take apart all of these features as we move along through our presentations. Just keep in mind that this is a summary of various elements of a class diagram on this specific page. There are various ways to read the diagram, and from this diagram it's possible to conclude that, for example, subscription reservation, which is represented by this box, can reserve several tickets, and that refers to the relationship to the ticket box right here. Individual reservation is capable of reserving only a single ticket. Right here again is demonstrated by having an individual reservation in relationship with the ticket, and we have some multiplicity indicators showing us that it's optional, but the maximum number of tickets per individual reservation is just 1. Every performance has many tickets available. Each ticket has a unique seat number. A performance can be identified by a show, a date, and a time. So you would expect a lot of interesting information from a diagram, especially if it really reflects the structure of the software that we're trying to build. Class notation. I already mentioned the overall organization of the UML is that when we have a box representing a software class, it is subdivided to 3 areas. The top part indicates class name, the second or middle part has data attributes, and the lower part indicates the operations. There is one specific notation for an interface. Interface is a formal definition of a contract with a list of operations that allows the class that implements the interface to provide concrete implementation of these operations. So there will be time when we discuss the interfaces in detail, but for now, just an example that an interface also looks like a box. Interface by definition can have no data, so you'd see that the data attribute box is empty, but it does list a set of operations available. And here is a class that implements the interface, and you see the punctured line with the triangular arrow shape. And this is an inheritance or generalization relationship, which also similar to this relationship, but this time the line is solid. So this is an inheritance. So in interfaces and inheritance have close relationships, and we will see examples of them in the future. So the primitive types include numbers and strings. Primitive types are passed around by value, and operations may return data values as results. Let me magnify this view a little bit. And in this diagram, we can observe the presence of the data types specified in various places. For example, the quality data attribute that is specified for the printer has a data type of an integer. The print operation, generally speaking, when it's italics, it represents the fact that the operation is abstract, not fully implemented by this class, but required to be implemented in the classes derived from it. But once again, it has the data attribute, and its type is a string. So print data, which is a string. So this is UML notation, and of course when you read the corresponding chapters of the book, they have a pretty good description of all the details about the data types as they're used with data attributes and the operations. From an earlier example of a box ticket class diagram, you'd realize that there exist different kinds of relationships between classes, and the groups of these relationships could fall into these categories, such as association, composition, dependency, generalization, and realization. For instance, we already saw a realization of an interface example. So taking them apart, association relationship provides description of a connection among instances of classes. This is pretty generic way of connection between two classes. The only thing that it sort of indicates that one class has access to another class, or one object has a way to access another object and be able to communicate with it. So it does not create anything special in terms of new structures or new rules in the programming language. It simply is that one of the objects has a pointer or a reference to another object in memory, and therefore whenever it wants to, it can use that reference or pointer to access another object and start using its operations. So that's just really very generic type of association. Overall, the vocalization of association can be provided simply by saying that one class has access to another class. We can say that a person has access to an address, for instance. Right, so person object of type person has access to an object address. And navigability is provided by an arrow. When arrow is present, basically the rule is that this object has access to this object, so you always follow the direction of an arrow. If that arrow was reversed, you would then assume that address has a person, which probably doesn't make much sense in the software design, but that's the way you would interpret the diagram, and it's navigability. So navigability is just a simple rule that when you have an arrow, that's the direction in which you need to be able to interpret the diagram. If the arrow is absent, so it's not present there, then navigability is both ways. You can go either this way or this way, and that's allowable. A composition association in a class diagram indicates that there is an object which requires presence of other objects to be fully operational, to be correctly configured and be functional. Such object is indicated by the rhombus shape. Let me resize this diagram a little bit. Now the rhombus, as you can see, can be empty or filled, and that creates a difference between the aggregation association and composition association. So what is the difference between aggregation and composition? In aggregation, as we said, the object requires the presence of other objects to be fully operational. For instance, subscription cannot exist without an event. Event has to be in place in order to subscription to be fully functional. However, the aggregation association, which is indicated by this empty rhombus, tells us that the timing of creation of two of these objects can be quite different. We can create an event and then later on create a subscription, or vice versa. But at some point we're going to establish this association and start using the subscription the way it's intended. In the composition association, which is indicated by a filled rhombus attached to the object that requires other parts to be present for it to be fully operational, indicates that all of these objects must be constructed at the same time, or generally speaking, you would expect that creation of all of these objects that are put into this association is done at the same time, and their life cycle is the same, and when it's time to dispose of these objects, it happens for all of them at the same time.